What we've seen by thinking about interactions so far is that when one variable is 0, we can interpret the slope of the other variable. And changing where one variable hits 0 alters the slope of the other variable. And so we strategically change where one variable hits 0 in order to observe how the other slope changes, so that we can get hypothesis tests that enable us to understand the interaction. In other words, conditional associations between one variable and our response variable at specific values of the moderating variable. But how is this process different from main effects when we just include two variables in a regression model, two or more variables in a regression model, adjusting for one another? I have a demonstration that attempts to make it visually intuitive what is happening when we include main effects in a regression model and how it's different from what happens when we include an interaction in a regression model on my website. And you can go to the URL shown on the screen in order to watch that lengthier video demonstration. But today I'm going to give a short synopsis of it. In that demonstration from December of 2020, I used a hypothetical data set where the observations were doggos, and some of them were fluffy, and some of them were scruffy, and some of them were small, and some of them were big. And the main response variable of interest was how much they borked. And so I'm describing the data on the screen right now. On the left, you can see the counts, the number of dogs that fell into each of these four categories. 25 of them, for example, were small and fluffy, and 95 of them were big and fluffy. And so it is noteworthy at this point that, for example, the big dogs were mostly fluffy and the small dogs were mostly scruffy. And that is a clue about what's going to happen when we fit the model. And the mean values of their borks are shown on the right side of the screen. The borkiest dogs seem to be the small fluffy ones, and the scruffy dogs were less borky on average. I could represent this information about the data by plotting the actual observations. And so I've shown such a plot here. On the left, we have the small dogs. On the right, we have the big dogs. The blue dots represent the fluffy ones, and the red dots represent the scruffy ones. And the y-axis, of course, is their borks. And we can see what we already know from the previous slide, that the small fluffy dogs borked the most, followed by the big fluffy dogs, and the scruffy dogs borked less in general. And also that there's a lot of big fluffy dogs and a relatively large amount of small scruffy dogs in our sample. Usually, when you have observations like this based on categorical data, the clusters of observations will not separate so cleanly. They will overlap, and the effect sizes won't be so large as we see in this example. But I made the effect really dramatic in this case because it makes it much easier to understand what's going on visually when we look at a plot like this. The horizontal spread of these clusters is arbitrary. That's just a visual tool to make it easier to see what's going on. All of these points, their vertical height represents the actual borks from those dogs. But all of these points spread out horizontally actually are just in the small scruffy category, and so they would be in a straight vertical line if we plotted them literally. And when I do the regression model, it will be treating them as a single category, as though they were plotted in a straight vertical line. So I'm just spreading them out here horizontally so that we can see it easier. And I'm also showing the sample sizes and means for each of these four clusters on the screen, which is easy to do because the point's so cleanly separated. So for example, here, there are 95 blue dots because there are 95 big fluffy dogs, and the mean borks for this cluster of points is 43.31. The same goes for these other clusters. I'm going to show three regression models one at a time, illustrating what's going on with this data set. And the first regression model is the simplest. It's a simple linear regression model with size predicting borks, and that's it, completely ignoring the fur type that the dogs have. So as you know, we get an indicator variable for size in R that's called size big, which is the result of the default contrasts that R applies to a factor like size, where 0 is small and 1 is big. 32.25 is the mean borks for all the small dogs, and 6.88 is the difference between that mean and the mean for the big dogs. But it doesn't precisely represent any of the means shown on the screen. Here I've drawn that regression line from that simple linear regression model, and it passes directly through the mean of the small dogs and the big dogs. But it doesn't pass through the clusters for the small dogs, for example, because of course the mean for all the small dogs together would fall somewhere between these two clusters. So what this regression line shows is that ignoring fur type, the big dogs borked more than the small dogs did. The overall mean for the small dogs was 32.25, and the overall mean for the big dogs was 39.12. 32.25 is the intercept that we got from that regression model, and 6.88 represents the difference between this 32.25 and this 39.12. So there's nothing wrong with this regression model. It answers the question that we asked, which is what's the overall difference between the big and the small dogs, completely ignoring their fur type. But now let's ask a slightly different question. Let's include size and fur as two simultaneous main effects in this regression model. Both predictors are going to be in the same regression model predicting borks. This is what we get when we fit that model in R. The intercept is 54.56, and the slopes are negative 9.9 and negative 31.6. Here's a plot of those slopes using the dotted lines. The slope in both cases is negative 9.94 because it's constrained to be the same. There's only one slope for size, not two. So there's not a separate slope for the scruffy dogs and the fluffy dogs. Instead, we have one slope drawn in two locations to reflect the main effect of fur. These dotted lines represent one slope for the size variable. It's like I had held two pens in my hand an equal distance apart, and I got one swipe across the paper in order to draw both of these fit lines. The location and angle of these two lines is the result of doing that thing with the pens where they're equal distance apart and I only get one swipe across the paper in such a way that it minimizes the sum of the squared residuals. So the slope of negative 9.9 represents a compromise slope. It's the relationship between size and borks adjusting for the fur type, but it doesn't pass directly through the means of any of these clusters because it is constrained so that it's a single slope at a single angle, and the two of them drawn on the screen can just be a certain distance apart. So we had to compromise and make it fit as best we could, even under the constraint that it had to be a single straight line. And the difference between these two lines, the distance we held the pens apart, is the negative 31.62. That is the difference overall between the scruffy dogs and the fluffy dogs, again under the constraint that that difference is a compromise between what it would be if we were looking at the small dogs and the big dogs separately. So the slope of negative 9.94 is within fur type condition, but not within a particular fur type condition. It's sort of like a weighted average slope of size within all the possible fur type conditions. The third regression model that I'm going to show is an interaction model that has size and fur and the size by fur interaction. And of course, it's easiest to understand the size by fur interaction if we include a version where the fluffy dogs are the reference category, like here, and a version where the scruffy dogs are the reference category, like here. So we can see that the slope of size in the fluffy case is negative 16, and the slope of size in the fluffy case is only negative 1.6. Here are the lines from the interaction model drawn on the same plot. The solid lines stem from the interaction model. The dotted lines stem from the two main effects model. And I've shown the means on the screen again because now these solid lines pass directly through those four means. This red dot represents a mean of 20.87, the actual mean of the small fluffy dogs. And this blue dot here is 43.31, the actual mean of the big fluffy dogs, and so forth. The interaction model is the one that connects the dots of the means of all the clusters. The slope of size in the fluffy condition is steep, negative 16, like we saw in the previous slide, and the slope of size in the scruffy condition is relatively shallow. Here I've moved the plot over and put that output from the previous slide just with the slopes on the screen so that you can see. And the slope of size is negative 16. And the blue line has a slope of negative 16, and the red line has a slope of negative 1.6. Because these lines are allowed to have different slopes by the inclusion of the interaction, now the least squares algorithm can actually make them connect the dots of all four means. So 59.56 is the mean for the small fluffy dogs, and it's the intercept from this version of the model up here, where the reference category is the small fluffy dogs. 43.31 is 16 points below that 59.56, consistent with this conditional slope of size in the fluffy condition. 20.87 is the intercept from this model down here, where the reference category is the small scruffy dogs, and 19.25 is 1.6 below that, consistent with the conditional slope of size in the scruffy condition. So here's a review of all three of those models. When we ignore fur type and just fit a model with size predicting Borks, we connect the dots of the two overall means of small dogs and big dogs and see that the big dogs Bork more. But then when we adjust for fur type, we see that there's an overall negative association between size and Borks within each of the fur type categories, or at least within the fur type categories individually, but then compromised between them. And the reason we saw a positive slope in the simple linear regression model is probably just because there's a bunch of extra fluffy big dogs. And finally, when we include the interaction in the model, we get a pair of lines that passes through the means of all four groups. The main effects version is like a compromise between the conditional slopes from the interaction model. The best slope for the fluffy dogs alone would be this solid blue line from the interaction model. It passes directly through the means of the small fluffy and big fluffy dogs. And the best slope for the scruffy dogs, the one with the smallest sum of squared residuals, is the solid red line. It passes directly through the means of the small scruffy and big scruffy dogs. The dotted lines are what we get when we fit a slightly simpler model that does not include the interaction but just two main effects. And it's like we were forced to hold two pens equal distance apart and swipe them across the page just one time in order to draw both lines. They represent a compromise between what the best slopes would be for the fluffy and scruffy conditions, kind of like a weighted average of those two slopes. We use main effects like that to get a sense of what the general association between size and Borks would be if we already knew the fur type of a given set of dogs, but we didn't know which one it was. We wanted sort of a general sense of how size is associated with Borks, adjusting for or given information about fur type. But we didn't want to get so specific as to say which fur type we were talking about. Let's look at one more quick example, going back to the coffee and math tests example from earlier in this class. Imagine a correlational study where participants in a math class reported whether they had coffee before a test and how many minutes they studied for it. We're going to model the math test percentage score as a function of coffee, which is binary, yes or no, and practice, which is continuous, the minutes of studying. I made some fake data consistent with this hypothetical design, and I made it so that coffee and practice were correlated. People who studied longer were also more likely to drink coffee, but we're interested in seeing whether either of those things are correlated with their math test percentage score, and not just correlated on their own, but whether they're associated with math test percentage score adjusting for one another. On the left, a scatter plot of math test scores and minutes of practice among those who did not drink coffee. On the right, a plot with the same axes, but among those who did have coffee. You can see that people who drank coffee also practiced more on average. Their minutes of practice are farther over to the right along the x-axis. So we might want to adjust for coffee when determining the relationship between studying and test scores, and adjust for studying when determining the relationship between coffee and test scores. Otherwise, any association between studying and test scores might just be due to the coffee, since studying and coffee are partially confounded. So let's look at a regression model where test score is the response variable and we have two predictors, two main effects, coffee and practice. Here's that regression model. The intercept, 50.87, represents the fitted value for participants who did not drink coffee and had 0 minutes of practice. The slope of coffee, 6.37, represents the relationship between drinking coffee and test scores on average at any fixed point along the spectrum of practice. In other words, participants who drank coffee scored 6.37 units higher on the math test, given a fixed value of amount of practice. And the slope for practice of 0.13 represents the linear relationship between practice and test scores given information about coffee or adjusting for coffee. We could imagine looking at the association between practice and test scores among those who did not drink coffee and among those who did drink coffee. And if we found a compromise between those two slopes, if they were somewhat different, that compromise would be 0.13, meaning that practice in general was associated with higher test scores, given that we already know the information about whether the person drank coffee or not. So the regression function for the estimated math test score is this. Estimated score is 50.9 plus 6.4 times coffee plus 0.13 times practice. And we got these three numbers as a result of finding the values that minimized the sum of squared residuals. In other words, that kept the estimated scores as close as possible to the actual scores. So I'll draw the results of this model on the scatter plot. This line stems from the model we just looked at, the one with the regression equation shown at the bottom of the screen. It's the same line on both scatter plots, just raised or lowered to account for the overall difference between coffee and no coffee. And as we just learned, this is not the same as fitting a regression model separately on each subset, because this representation holds the slope of practice constant regardless of coffee. These are two cross-sections of the same regression plane, not two separate regression lines. This is another instance where we can imagine that we had to draw both lines in one stroke while holding two pens. They are constrained to have the same slope, so they have to be a compromise between what the slopes would be if we estimated them separately. Both plots show estimated scores equal to 50.9 plus 6.4 times coffee plus a slope of 0.13 times practice. So on the left, the estimated score is 50.9 plus 0.13 times practice, since coffee is 0 there. And on the right, it's 50.9 plus 6.4 plus 0.13 times practice. It has a higher intercept, the same slope. You can think of it as a higher intercept because it has the coffee factor built in. What if I want to see if the relationship between practice and test scores differs depending on whether the student had coffee? Of course, I would add an interaction to the model. Here it is with the interaction term. Notice that the interaction is not statistically significant, but not 0 either. The slope for coffee, 12.90, represents the estimated difference between no coffee drinkers and coffee drinkers for those who did not practice at the reference point for practice. And the slope for practice, 0.17, represents the linear relationship between practice and test scores among the group that did not drink coffee. How would I find the slope of practice in the coffee condition? Well, I would need to use a different dummy variable, one where coffee is 0 and no coffee is 1. Let's try it. Here I just manually created this alternative dummy variable, no coffee, that's coded so that coffee is 0 and no coffee is 1. And the slope of practice, 0.07, is shallower and not statistically significant. When we were looking at no coffee drinkers, practice had a statistically significant relationship with test scores. When we're looking at people who drank coffee, practice did not have a statistically significant relationship with test scores. And yet the interaction is not statistically significant either, implying that the relationship between practice and test scores was not significantly different depending on whether the student drank coffee or did not drink coffee. This illustrates a key point. The slope of practice was highly significant for the no coffee group and not significant for the coffee group, yet the interaction is not significant. A slope like we got in the no coffee condition would be very unlikely to arise due to chance if practice and test scores were unrelated. This slope on the screen now for the coffee drinkers could arise due to chance 23% of the time if practice and test scores were unrelated. Yet the difference between the two slopes is not significant, which is the same as saying that the interaction is not significant. In other words, a gap between the two slopes as large as the 0.10 gap that we observed here could arise due to chance 24% of the time in a world where the two slopes are actually equal. A key general principle is that it is totally possible for one slope to be significantly different from zero, yet not significantly different from another slope which itself is not significantly different from zero. Here are those two slopes plotted. Notice here that the slope on the right is shallower than the one on the left, just as we saw in the model output. Both slopes now fit their respective scatter plots better than they did when we omitted the interaction from the model and constrained the two slopes to be equal. These plots are equivalent to what you would get by fitting regression models separately in the no coffee and coffee groups. The hypothesis test not necessarily equivalent, but the slopes equivalent to that case, because the interaction term allows the model to fit separate slopes to each group. And then when it applies the ordinary least squares algorithm, of course those separate slopes fitted for each group will be the same as the best fit lines through those groups. For visual comparison, here's the plot from the model with a main effect of coffee and a main effect of practice and no interaction. The line on the right is raised up a bit due to the main effect of coffee, but it is at the same angle as the line on the left, because the main effect of practice is constant regardless of coffee. Now we'll toggle back to the slopes from the interaction model. They're now tilted differently. This is true even though the interaction was not statistically significant. Including an interaction in the model, even a small one, releases the constraint that the slope of practice must be exactly the same in the coffee and the no coffee categories. It allows us to draw each line with its own pen instead of having to hold the pens at the same time and make one swipe across the screen. This main effect slope is a compromise between what the individual slopes would be from the model with the interaction. Okay, I know this was a lot of information and a lot of examples with different kinds of variables. It takes a lot of practice to get used to interpreting regression interactions, and even regression main effects for that matter. In fact, sometimes I think main effects are more complicated than interactions. So it's okay if you're just starting that practice. It doesn't all have to fall into place right now. But I do want you to remember a few key points. When there's an interaction, the conditional slope of one variable is estimated at the point where the other variable is zero. And if we strategically change where one variable hits zero and watch how the other slope changes, we can understand the interaction. And main effects from a model that does not have an interaction in it are like a compromise among the possible conditional slopes that you would get if you did include the interaction.